Hi, how's everybody doing? Hopefully everybody had a good lunch. So we're ready to get started here again. Next session here, we're going to explore some of the, I need this, hang on. Next session here, we're going to explore, let's see if we try one more time. We're going to explore we're going to look at a large soccer event happening here in North America in 2026. So my name's Pete Emminger. With me here, I have Lukas Schaufler from Lavo. He's the Senior Director of System Architecture. He's responsible for designing and building broadcast infrastructure, heavily COTS-based, which I think will be of interest to this group here. He's also responsible for the technical pre-sales group and system engineering. Dan Murphy, to his right here, is he's with NEP. He's the VP of platform at NEP. He was the founder of a platform that's been talked about. He talked about it this morning called TFC. And I think everybody who's been here today kind of understands Dan from his role this morning. So my name is Pete Emminger. So I was the former global CTO at NEP. In addition, I spent some time at Activision Blizzard. I've been heavily focused on the general shift in the live broadcast and live event space to COTS, software, and cloud for a number of years. So what I'd like to do to start is kind of just explain, when you look at a large international sporting event, it's really important to go all the way back to the venue. So a lot of people focus on cloud, the data center, the processing environment, but you really have to start at the venue. Sports originates from a physical place. It doesn't, come from the cloud. It comes from physical stadiums, physical cameras, physical places. So this event in 2026 is spread out across North America. It's spread out into 16 venues in 3 countries. You can kind of see the basic overview here. It's pretty geographically distributed. This is a pretty American audience, so it should be pretty obvious, but some of these venues are thousands of miles apart from each other. It's also important to note there's a central facility that we'll talk about in a minute that's based in Dallas in 2026. All of the video is going to be one sort of house format, you might call it, and that's 1080p 5994 HDR. And all of the audio content is produced in multi-format, and that's because the different distribution partners have different audio distribution capabilities. Like I mentioned, sports originates in a live stadium. It's important to understand sort of the scale and sort of how things get from the field. So from a video perspective, most of the matches, 33 cameras, it does go up in camera count up to 46 once you hit the quarterfinals. And you can kind of see on the slide there, you can see the overall general camera plot or camera layout for all of the cameras that are at a typical match. In addition to the cameras, there are 56 microphones. So obviously you can't have a sporting match. You can't watch without audio. Audio is really critical for user context in any broadcast. 56 mics, combination audience, ambient, field of play, camera mics, wireless microphones, commentators, a fair amount of audio sources go into your typical live sporting event. So all of those signals from the venue and from the stadiums have to go somewhere. And so there's a pretty extensive venue contribution network that links all of the venues to the IBC that I mentioned earlier, the International Broadcast Center. So the International Broadcast Center, for people who are not familiar with international sports or large sporting events, is essentially like a central combined facility where all of the technology, all the feeds come together into one place. In this case, next year in 2026, it will be located in Dallas. It's being built out in the convention center in Dallas. And you can kind of see it's basically a temporary hub for a number of really key facilities and really key components that make up, how the event is supported and distributed. Some of those include the master control room. So, this is essentially all of the feeds coming in and out, all the feeds being monitored. It's important to note that while all of the main production feeds from the venues are being distributed back to the IBC uncompressed, all of the camera feeds come back. So there's a pretty substantial amount of monitoring and redistribution. All of those feeds, though, come back compressed. So only the main program feeds come back uncompressed. There's also a quality control room, and there's audio control as well. All the matches will be produced all the way up to immersive audio, 5.1.4. So there's a real need for audio control rooms in the IBC. So a program of this scale and a project at this size, it can really only happen with IP. This really wouldn't be possible, like, as things have transitioned away from SDI and other analog sources and into IP, it's really a critical enabler. And so Lukas is going to go through some of the specific technology that overviews that.
So in this case, it's actually a mixed format. So you have 2022-20 and -22. And all of those stage boxes are also, of course, locked to GPS. There is an additional transcoding from MADI to 2110-30 for the audio signals. And all of those signals are then going to the IBC. So in this case, we're talking about the multilateral feed. We're talking about all cameras, and we're talking about the microphones. So very interesting is that when the signal hits the IBC, all of the replay is done at the IBC and fed back to the trucks. So the trucks themselves don't do the replay anymore. Same for the entertainment feed. So the entertainment feed is the feed that you see on the video walls in the stadium, on every single TV that's somewhere around there. That's all actually produced at the IBC and fed back through the same stage boxes to the truck and then also distributed at the venue. Why is this done? Well, it's pretty simple. As Pete said already, there are thousands of miles between venues. You would have to equip each venue with all the necessary equipment. Since we only talk about 6 games per day at max, it's actually just more feasible to have this all at the IBC. The second part of the connectivity between the IBC and the venues is the TOC area. So that's the area where local and national rights holders can pick up their signals. So there's an additional set of stage boxes there to provide that functionality. When we look a little bit into the stage boxes themselves, so it's all done on edge devices. You see, if you combine everything together, we are talking here about a decent size SDI distribution network, actually, with up to 14,500 signals roughly. And all of that is actually handled on the same devices. So we're talking about audio, video, and ancillary data. You will also see that on those 16 venues, you only see 10 actually of the stage boxes for truck connectivity, because some of the trucks will provide the IP feeds natively into the IPC, and the NEP trucks are part of that. So of course there's tons of signals, right? They also will need some audio and video processing, and the audio and video processing for this event is done on COTS server hardware. So we're really talking about decoupling software and hardware. And the overall aim is to reduce the footprint and the bespoke nature of dedicated functions for each device. So basically the customer doesn't want to have now a dedicated audio core, dedicated UDX converters, dedicated frame syncs. So the whole solution here is really based on containerized applications, software only. And just for completion here, I'm showing here Supermicro server, but we are talking here about COTS, so it could be Dell, could be Lenovo, could be whatever. And just a nice side story, why the customer chose also to stick with that. So there were, of course, tests that we did before with the platform. I like to tell that story. There was, in Spain, there was an event where they really just last minute realized, oops, we forgot that we have another audio mix that we have to do. And it was really last minute, that it was game day. And really the possibilities that you had, like engineers just remoted in, created that app, connected the signals, and they were up and good to go. If you would do this with like traditional setup, well, you have to get an audio core up there somewhere to your venue. So that actually shows the power of the platform that they've chosen to go with. All of the processing is actually done at the IBC itself. I will present some of the apps and some numbers to it. And as it is right now, this is all done in only 56 servers. It's 192 core EPIC-based CPUs that are used in those servers, and they all have 100 gig redundant network cards in there. So looking at the apps a little bit, what has to be done? So as we said already, there is a mixture of 2110-20 and -22. So there will be, or there is also the need to transcode between JPEG XS and native 2110-20 or uncompressed signals. So for that purpose, you need to have, of course, the apps that will transcode that. You see there is a total of 678, if I can read that correctly. It translates basically to 113 transcoders per venue, as there is only 6 venues that are operational at any time of the day. The whole JPEG XS transport is done based on TR8 in a 10:1 compression. And just to recap, so the multilaterals, I'm not getting out this word, I'm sorry, cameras and all the audio feeds are coming from the venue, and then to the venue you send the unilateral feeds, which is the pickup points for local and national broadcasters, the entertainment feeds that are going to the stadium and the TVs, and then the replays that are going back to the truck. Now, as Pete already mentioned, there was the choice made to run in 1080p 5994 with HDR. There were some extensive tests that led to the belief it's better to utilize all available bitrate and go for HDR rather than using 4K. So by a lot of transcoding tests, up, down scaling, etc., it was just like realized that's the better choice. For that, of course, we don't have every device and every rights holder on this world has HDR already implemented in their signal chains. So for that, you have to need to transcode it between HDR and SDR. And here's also another thing that comes into play for the platform. So you also have rights holders, an example, that are still running on 1080i. So you will see in the presentation slide, I'm writing 220 combined color correction and UDX paths, because what is actually done is that if you have a rights holder that needs a specific format that would not be done by a color corrector, it would be simply replaced by an up-down cross converter. That also means that you can very flexibly react to your production demands based on whatever rights holders are booking your signals. You can choose what you really need and want. And that makes it also very efficient from multiple perspectives. First of all, an up-down cross converter needs more processing power than a color corrector. Second of all, an up-down cross converter costs more, right? There is more functionality. So in this case, they are able to really dynamically react to the needs and being able to fulfill the needs really based on a production demand, and they don't have to calculate for the worst case possible. Last but not least, actually I was lying, it's not the last. There is an intelligent multiviewer. So of course, we talked about 14,500 signals. Those need to be monitored. There is a lot of stuff going on. Therefore, a multi-viewer solution is there so also in place. Totally, we have 232 heads with around 1,030 unique IP signals that need to be monitored at any point in time. And this is where the intelligent multi-viewer, also software-based, comes into place. And what this multi-viewer basically does is it has an additional workflow tied to it, which is called the proxy workflow. So every signal that actually is fed to the multi-viewer will first be proxied into 4 separate proxies. So you have what a proxy basically is a downscaled version of that picture. And then the intelligent multi-viewer determines, based on the geometry of the PIP on the layout, which resolution it needs to fulfill. Right? If you have a 4K monitor or a 3G monitor, you don't actually need full resolution because you never will be able to display it in the first place, except if you're like in a full screen layout. So that's where the proxy workflow comes into place. And then, of course, Labo should be known also a little bit with their background in audio. So we're also doing immersive audio mixing. So the trucks themselves, they actually provide a stereo signal, and all the immersive audio mixing is done at the IBC, and there's 2 types of immersive audio mix. So one is the close ball mix. So if you ever watch soccer on TV, you will realize that when they kick the ball, it's pretty loud. And that's exactly what the close ball mix is. So it focuses on the ball, all the action sounds that you can get from the field, as well as player interactions, as long they're still presentable to TV. And the next one is the field of play mix, and that's also very interesting. It's actually a fully automated mix with the click system. It's an algorithm-based solution that basically determines the position of players and the ball on the field and provides a mix based on this information. when you take 14,500 SDI signals and translate that into 2110, then you separate those signals with video, with audio, and metadata. So the system has quite a significant size that needs to be managed. And in this case, Lavo Home and VSM take over the control portion of that signal management. So we are really talking about all the routing, XY routing for the multi-viewers, for local operations. We're talking about tellies. We're talking about labels. So there's a lot of logic and complexity involved with it. That solution as it is available to the engineers at the IBC is really they just select a venue and one of 6 possible slots they have. And all the routing logic behind it is actually done by the broadcast controller. So it's not like that anyone has to go in and verify every single signal, do all of the routing. It's really a complex logic that's applied there to connect everything from the venues to the venues, back and forth, tally labels, etc., etc. There is roughly 230 operator positions that use some kind of an interface, either a tactile panel or software panels. They are all customized to their needs. So different positions need to have different signals and access, but also different functionality, which goes not only from XY routing, also to, controlling the color correctors, the parametric values, etc. of all of those devices. So they get that in access there. Last but not least, the VSM system also connects to each individual truck on a tele level. And that was necessary because at the IBC, we said before, they do replay and they do the entertainment feed for actually the video walls, etc. So with that, of course, the camera operators as well, the operators in the truck need to have the information that the signal is used outside of their production environment, basically. And therefore, the VSM control system is also used to tie to the trucks then with their local controllers. And it's up to 786 unique camera signals that system has to manage for that purpose. Yeah, and then also tying to a little bit to what you said in the morning today, all of that is driven by automation. It's not fully automated, but a big portion of it. And in this case, Netbox is used as the source of truth. So in Netbox, all the devices, all IP-based products are actually added there and entered, and it's providing the single data repository during the planning and the deployment of the project. And of course, since you have that possibility already, and we are talking here about, software-based platforms, you also add automatically the possibility to utilize automation. So what is done there is actually Netbox templates are fed into Terraform and Ansible, which then configure the devices based on the template information that's in there. Based on a production we did this summer with the same customer, the feedback was pretty great. Words like increased availability, reduced configuration workload, and also the allowing for rapid changes even in the post-deployment. So saying we commissioned everything already and then minor changes had to be applied. Automation here was really the big factor to make that happen. It's quite impressive what the new technology actually provides and what possibilities you have to actually run into an event like this. Last but not least, we also mentioned it's a quite big distributed network that has to be considered here as well. And for that, I'm actually handing over to Dan Murphy to talk a little bit about how TFC plays a role in that.
Yeah, so that level of complexity and that level of needing everything to work together doesn't just happen in one vendor or with one supplier. There are multiple suppliers who our joint customer relies on to deliver this solution. And the important thing is that all of those suppliers work together. There's obviously a very close relationship between us and Lavo, who are providing the processing and the broadcast control. And this is super important, but things like the NetBlocks source of truth, that needs to survive to everyone. So we use the same NetBox to provide all of the information for our own infrastructure as code, so our own Ansible and scripting that configures the network side, it uses the same data source as the information that the processing uses for making sure then that when we create an application like a UDX or a multi-viewer, that the information that we've sourced it from, where I configure the network port, where you configure the processing, it comes from the same place. And if we need to make changes, then we both run each other's scripts and we get a guaranteed reliable result. And that is exactly the point of doing things in a codified way, so that it is an automated process that is reliable and reproducible. So NEP is providing the network orchestration. So we're using our SDN tool, part of TFC, to provide that. So where Lavo brings the gateway and processing functionalities, and VSM provides the overall routing and broadcast control functionality. So you can think of that as like the user interface or the front end that the users all use, and it has its own business logic that will handle kind of the tally levels and to handle all of the interaction. Under the hood, we have a network that needs to be configured and an actual physical path that needs to be created, and that's where we come in. So VSM integrates with us using an Ember Plus matrix. So we expose a giant big northbound matrix, which allows VSM to tell the SDN controller, I need this signal in this place to go to this place. This is not just doing media and 2110-20-22-30-40 flows. This also works for data circuits, because one of the facilities that have to be provided for the customer is being able to route data circuits from place to place. And these are essentially network traffic circuits of certain sizes, 1 gig, 10 gig. And these need to be routable, where you can say, I want this network port to be able to be connected to this network port to be able to provision circuits for rights holders. And this is also done from VSM, where we present an XY matrix that says, here's all our source ports and here are our destination ports. And that allows MCR to connect those data circuits on bookings dynamically throughout the tournament. So TFC then has exposure to the devices themselves as well for monitoring what's happening on a traffic level, and also for using protocols for configuring and stitching up those traffics. The network itself is quite big. So, and it is not the traditional kind of, small air-gapped red-blue network. In fact, to get a reliable network of this size and to connect all this together and to do it in a very secure way, this is why you need a software network controller that will ensure that the traffic is managed well, make sure that the bandwidth is available to give quality of service to all of the different circuits that are happening there. And this is done in what we call a purple network, where it's a multi-spine. So it's a multi-redundant N+X network. So in this case, there's actually 11 spines going to be in use to provide the distribution across all 16 venues, plus IBC, plus all the other facilities that have to connect. And wherever you are in that network, we will expose the functionality to be able to get from source A to source B. For the private parts of the network, these are managed in private control spaces, but we also have to connect to foreign networks. So that would be OB trucks that are running their own facility that are connected into the network, and they may be connected directly into the network through a 2110 connection to actually expose -20 and -22, -30 signals. And that has to be handled in one way. And then there is also the management connection that Lukas mentioned, to be able to exchange tallies and a routing. So one of the things that needs to happen is inside of each OB truck, we need to be able to select sources at the IBC to route back through destined paths for confidence monitoring and for preview of what's happening inside of the IBC part of the network. And so there's actually router control that is happening between the local OBs and the VSM running the routing at IBC. That management traffic happens through firewall management's connections. So that is a fairly simple approach to getting the management. But for the 2110 traffic, when you actually need to connect two 2110 environments that each have their own PTP clocks, that each have their own streaming, they might have their own multicast, their own IPv4 addressing, that has to be handled slightly more sensitively. And so what we need is a demarcation in between and a natting that takes place, a multicast natting that takes place. And so what we have is a demarcation switch, which will present to the foreign network as an NMOS device, which will allow that device, that truck to basically see the network as a sender of a bunch of 2110 sources, exactly the same way that any NMOS edge device works. So it's just an NMOS node that exposes itself, and vice versa. So it'll have a whole bunch of receivers that will allow that facility to patch 2110 into the network. From there, that network switch will then translate that using multicast natting so that it's SCOM and G natted into a range and an IPv4 address scheme that matches the whole IBC network or the whole event network. So that means that the truck that is providing 2110 can have its own IPv4 schema, its own multicast addresses, and can independently provide those feeds 2110 into the network. Also means that we have a secure demarcation point where we can then ensure that no traffic from that truck, that network, can affect or hit the event network, and vice versa, where anything that's happening inside the event network can't be influencing or affecting or reaching. So it becomes a hard perimeter between both networks. And this was a very successful demarcation solution that we actually created for a similar soccer event 4 years earlier in a country in the Middle East. And so this is an important collaboration because these things have to work in harmony. We have to have VSM and the SDN controller work together. So we're not just using common protocols like 2110 and NMOS, but we're also having to work together and use single sources of truth, provide the same philosophy and the same kind of cooperation around the operations of the event to make this successful.
Yeah, thanks, Dan. That's a really great overview. I think also the last thing you said really points out the thing that you ended your keynote with this morning, which is teamwork is absolutely critical. It's like the most important thing. It's actually more important often than the technology. So I'd like to point out, as earlier was also true, the QR codes on the walls, you can scan them and you can input questions, and we'll be able to take some questions from the audience. So just scan the QR code, put it in, and it will show up here for me. But first, going back to the teamwork thing, I'd like to ask you guys one question, which is when we were prepping ahead of time, you were specifically talking about the intelligent multi-viewer, and specifically how both Lavo and NEP had to work together really closely to make that really work in an SDN environment. And so maybe one of you or both of you could kind of just talk on that very briefly, because I think that's, it's a new product, it's a new technology, and it's kind of unique to use it over such a large geographical event.
Yeah, I think one of the challenges of an intelligent multi-viewer, generally a device that will request streams by itself in an SDN-controlled environment, is a challenge that needs to be solved. So in traditional IGMP, the edge device is actually the one requesting the multicast group from the switch, and the switch takes care of all of that. In an SDN-controlled environment, it's actually the SDN controller that determines at which point from which switch port to another switch port, basically the traffic is flowing. So there is an information exchange necessary to actually introduce the information to the SDN controller. Hey, I'm actually not interested in the full res picture. I'm actually interested in the 1/64th resolution picture of that.
Yeah, and I think that's where it's important to be aligned. And one of the unique things about the intelligent multi-viewer is that it's not just mixing proxies, it's also mixing different types of media, because you can also route the JPEG-XS directly into the pips. So there is different behavior based on the different sources. So there's a level-based logic that takes place. So if you're in the compressed level and you're routing -22, it behaves in a certain way. If you're in an uncompressed level and you're routing -20, that's a different methodology. And also one of the sort of unique things about the .edge providing the NCAP is when you're NCAPing on -20, it can automatically create the proxies in the actual edge device. So you don't need to do a separate proxy conversion. It can happen at the same time as it's doing the NCAP. So in reality, there's actually 3 different ways in which the content can be generated. And when a user and an end user is going to route, hey, I want camera 1 in that pip, they don't care where that camera 1's coming from, but we need to know that it's either a JPEG-XS, it's a NCAPed on a .edge, or it is coming in -20 and it needs a proxy to be generated. And this is a process where both of us then align ourselves on the business logic required for that, and make sure that we can deliver that.
Great. I mean, it's definitely pretty interesting. So let's move on to some of the questions from the audience. So I'm going to start with the first one. So with proxy being used for multi-viewer, do you run the risk of introducing problems or unexpected issues because you are not really in the actual video feed being monitored?
Yes and no. That's the perfect answer. So in the end, yes, you're manipulating the signal. And the moment you're manipulating the signal, you're not working with the original source. What is very important to mention here is actually that .edge, as an example, doesn't transcode that onto a TDM bus. It is a packet-based router. And what actually at the proxy generation level happens is that certain pixels are dropped. So there's no recalculation happening, which would falsify the information. It is really that some pixels are dropped based on the raster size that you have. That said, yes, you're still running through a device. The device is still a point of failure. Right? You can build that, of course, also redundant, because you can fail over to another device that can generate the proxies for you. So from a technical level, you do not falsify the signal. You just remove some pixels. From a practical level, yeah, if the device is dead, you will have to react.
But I think also this is one of the fundamental things with IP. At the end of the day, if you are NCAPing, if you're decapping your source at the receiver level, even in -7, the packet merge is happening independently in every device. Whether the packets have actually arrived from that device, it is already, that is a technical challenge in IP, no matter whether you're doing a multi-viewer, even just rasterizing the picture onto a multi-viewer means that you are changing and manipulating the signal. Any RTP receiver doesn't necessarily behave the same way as another RTP receiver. So this is why fundamentally observability is critical in an IP network. And as we would expect, .edge provides a large amount of observability. So part of the functionality that we provide on a network level is monitoring every packet going in and out of the network. We also have network probes that allow us to, at different points in the network, so at both the venue side and at the IBC side, we have dedicated network probes that allow us to bring traffic in and inspect the traffic at that point in the network. In the edge devices themselves, we collect all the telemetry. All of that goes through a massive monitoring telemetry engine with a bunch of monitoring services. And if you walk into the IBC, one of the things that you're going to see is giant Grafana dashboards that summarize that information. And it's an aggregation of lots of things. It's logs, syslogs coming in. It's logs from switches, logs from edge devices. It's telemetry coming in, packet counters, error counters. And this kind of observability is essentially a replacement for a traditional, okay, if I don't see it, it's not good. True, we need observability of the actual end products. That's We still want to monitor off air. I'm not saying we don't ever monitor off air. Of course we monitor off air, but it's just as important to monitor the technical statistics of what's going on and the telemetry of what's going on inside the system.
Great. Okay, another question. Does NetBox have awareness of the transport layer? And if transport problems arise, how does NetBox help heal?
So NetBox is a source of truth for how the network should be configured or how the system is configured, right the way down to even what rack unit a device is racked up into. But NetBox is not real-time monitoring. So for real-time monitoring, you go into the telemetry system I just talked about. That's, mostly Prometheus, Influx, Loki, Grafana, these kind of tool sets that drive the monitoring side of things in terms of real-time. Now, again, all of that is populated from the same source of truth. So if we go into NetBox and we say, hey, I'm going to swap out that edge for some other edge, then we can run our scripts, or we can run the configuration tools that will then propagate that information into all the various systems that need. So single source of truth for the way it should be configured, but NetBox is not a replacement for monitoring.
Great. Let's jump to talking about replay. So here's a question. I might paraphrase it a little bit, but basically, do I understand correctly that the replay is created remotely with the compressed signal, or is it remote operated and then locally outputted? I mean, basically, I think the question is, how exactly is that workflow working? Is it done off of a compressed signal? How's it getting sent back? What's the delay involved for the operators and the directors?
So to the delay, unfortunately, I don't have any data that I can share. It will be for sure fast enough. Otherwise, they wouldn't do it. When it comes to the replay itself, so we're really talking about JPEG access end to end on the replay and on the recording side. And all the replay operators are locally at the IBC. So everything happens on the IBC, and the truck basically just receives the replay. The coordination happens traditionally over the intercom. And I hope I answered the question.
In terms of latency, there's no additional latency in the compression layer because that's the whole point of the -22 mezzanine compression. It happens in the same amount of time it takes to do a frame boundary alignment on a normal RTP session. So you're not losing any time because of the compression. Obviously, we can't defeat physics. So there is a round trip latency, and that depends on the venue because the venues have a different amount of fiber. There's a different kilometer range between each venue. But we're talking ranges that are below perceivable thresholds. So shading, for example, also happening centrally. We can have central shaders controlling cameras, sending a shading message back to the site. So the CCU at the site is responding to the inputs from a shader's, RCP. And this is happening in a, let's say sub 100 milliseconds time period, which is, roughly speaking, in our experience, that sub 100 milliseconds is the perceivable time period. So most operators are not going to notice latencies up to around about 100 milliseconds.
Yeah, that makes sense. Okay, so interesting question here that's sort of non-IP, but why is there a need for 5,280 SDI connections at the IBC? Seems very high, especially considering all of the processing will be done by native equipment.
So not all of the SDI connections are used. They are just available. What is happening there is actually, as we said, Edge does proxy generation, so it has additional functionality added to the blade, but the SDI spigots are still there, so therefore they are still configured. It doesn't mean that all of them are going to be used fully, right? So the 14,500 SDI signals or SDI spigots is a theoretical number. It is an IP-based production, and on the handover points, there is SDI still necessary.
Yeah, and it should be noted that there's this tournament is massive. So there is a large interest globally, which means there's a large number of rights holders. Each of those rights holders want a significant package of signals, and the handoff for most people still is SDI. So we're not yet in an era where everyone rocks up with a QSFP or an OSFP 100 gig connection and says, hey, can I have my 2110 traffic? That's just not yet where we are. The vast majority of rights holders want a SDI demarcation point. And so, if you're doing 6 simultaneous matches and a typical package would have, say, 20 to 30 multilateral signals, all being handed over and then add some ISOs, add some, rights holder. They might have their own unilateral circuits running alongside that. You times that by 6, then times that by all the rights holders that are at IBC, you start getting to some pretty big numbers pretty quickly. So, it is a big tournament, and this used to be done with tons of DAs and 2 big giant SDI crosspoint routers and, racks and racks and tons of green cable. If you look at what we did 4 years ago, and if you look at what we are going to do next year, there's a definite progression and a definite shrinking of the footprint. And I guess one of the flexibilities of doing it this way is then you can give anyone anything anywhere. Whereas before, when we had tons of DAs and we had traditional ways of distributing this out, you were a lot more restricted in what you could hand off and what a rights holder could ask for. Now they can go to the, sales desk and say, hey, can I get this extra feed for this game? And MCR can just route that out there because the speaker's sitting there ready to go. So the flexibility definitely has been driven by the technology as much as the technology has driven the flexibility.
So on the 14,000 feeds, there's a good question, which is how much, if any, AI automation is used in provisioning them? And then a follow-up question to that is, do these feeds also include the OTT fast enabled endpoints like Roku? Maybe start with the first point. Any AI automation tools in managing all of these feeds?
So as mentioned already before, not necessarily feeds, but the devices that are transporting the feeds. So in the previous example, the Terraform and Ansible deployment took care of configuring all devices. I can speak here for one vendor, but of course there were other vendors involved. But it was configuring all of those devices as well as configuring the servers. So we're talking about the first birth of the servers, and then also deploying all of the containers on the servers. So as we spoke, right, there is a multitude of apps running. We have 780 something stream transcoders, hundreds of UDXs. So we are really in the range of thousands of apps. That would even not be practical to do it by hand. So this is the typical application where automation was used. Let's call it AI level 1 and level 2. But yeah, there's definitely more to it also on your side.
Yeah. I mean, in the only real machine learning, AI is kind of, what do you mean by AI? If we're talking about machine learning, we do have, in the monitoring stack, there is, learned, norms that can alarm on abnorms. So you do have some anomaly detection, which is starting to get into the realm of machine learning. But do we have GPUs running on site that are, automatically routing feeds or checking things? Not yet. It is an air-gapped event, so it is not directly connected to any cloud SaaS services. So everything we do is run on-prem and driven from on-prem processing. I think in the future, there is a role to play there, and we might have localized GPU with some, machine learning stuff that's happening, or some language models that are doing trawling through log lines and things like that. That's not currently in play today.
Great. Well, thanks to both of you. Anything you want to say just in closing here before we wrap up?
No, it's,
Well, thanks for having both of you. Thanks, Simti. Thanks for having all of us. We appreciate it. And, that ends the session, and the next session will begin shortly.
Thank you.